If you have not watched the intro YouTube video on this accident, you need to watch it before you proceed. The video shows what the pilot would have seen on departure all the way to the accident site. The gist of this accident is that an experienced pilot flying a high-performance aircraft had a controlled flight into terrain on departure. The accident report found nothing physiologically wrong with the pilot and no mechanical malfunctions of the aircraft. I decided to perform an energy analysis of this aircraft's turn to downwind to see if it would provide any causation. I had to write an energy state computer program, AEAT, to be able to handle all the calculations required. The program essentially calculates the three-dimensional flight path and energy states of an aircraft every second and the energy required to maintain a true airspeed, as well as a Google KML file to display the actual 3D in-flight trajectory and a 3D obstacle mesh in the crash area. Most pilots know that once an aircraft breaks ground, it is flying in the air mass, and that the aerodynamic performance is solely a function of its relative wind in the air mass. Total energy equals kinetic energy plus potential energy. The reference system for an energy analysis is the ground, not the air mass. Kinetic energy is determined from the ground speed, not an airspeed in the air mass. Because we are climbing out at max power, we know we have to control airspeed, v sub x, with pitch only. We must remind ourselves that the sole source of energy for an airplane comes from its engine. The impulse from the wind is negligible compared to that of the engine, contrary to common opinion. Pilots are well aware of the impacts of energy on aircraft performance. Takeoff distance is a prime example. Wind shears are also a problem due to kinetic energy deficits. What most pilots do not understand is that there can be significant energy deficits in departure turns to downwind with high turn rates and strong wind components down the runway. Kinetic energy is 1/2 times the weight divided by gravity times the velocity of the ground speed squared. The kinetic energy of an airplane with a strong headwind component is much less than a no-wind or tailwind situation. Ground speed equals the true airspeed plus or minus the wind component. Problems can arise when the aircraft TAS vector changes rapidly in relation to the air mass vector, i.e. the wind direction. When this happens in certain situations, there is not enough excess energy available to accelerate to the new required true airspeed for flight without trading altitude or climb rate for airspeed. The larger the divergence in the air mass vector relative to the true airspeed vector, the larger the kinetic energy deficit can be. Now, this accident describes a 4,351-pound aircraft that departs runway 18 with winds at 170 at 14 knots. This is 326 pounds over max allowable takeoff weight. His estimated climb performance was 1,095 feet per minute. The pilot departed and started an immediate left turn to downwind at midfield in a, quote, better than 45-degree bank turn, unquote. The aircraft appeared to stall about 3/4 away around the turn and about a 90-degree bank, resulting in a fatal impact. We start with the following assumptions. The aircraft started a very steep departure turn at midfield, or very near midfield, and at a very low altitude. The witness stated that the bank angle was greater than 45 degrees, so we will build scenarios for both 45 and 50 degrees. Number 2, we do not know the altitude at which the pilot started his turn, but it was reported as extremely low, so we will assume it to be 50 feet. Number 3, we do not know at what airspeed the pilot started his turn at or held during the climb. We will assume it was v sub x, which is 90 knots for this airplane. We shall treat the takeoff winds as constant through the turn to downwind. And 5, the estimated climb performance will be adjusted from 1,095 feet per minute to 1,008 feet per minute. The 1,095 feet per minute was based on a max gross weight of 4,100 pounds. We need to adjust the 1,095 feet per minute for the excess weight. The aircraft is 7.95% overweight, therefore the climb rate would now be reduced to approximately 1,000 feet per minute. The point where the turn to downwind occurs was reported at midfield. This is a very imprecise observation and could easily be plus 1,000 feet. The distance from the liftoff point to the start of turn is 2,840 feet. Raising the gear and flaps in this interval seems realistic, the point being that you would think he would wait to start his turn until his gear and flaps were up. 7. It takes 1.56 Gs to maintain a 50-degree bank turn and 1.15 Gs for a 30-degree bank turn. If the pilot maintained only 1.3 Gs in the 50-degree turn, that creates a reduction of 500 feet per minute, which makes the VVI 500 feet per minute for the climb instead of 1,000 feet per minute. Failure to maintain the proper G level can result in significant decreases in climb rate. We create scenarios for both 1,000 feet per minute and 950 feet per minute to account for poor G control. The accident reports that the aircraft clipped 4 feet off the top of an 80-foot tree. These pine trees can grow to 150 feet. We will generate obstacle messages for 85, 100, 125, and 150-foot AGL obstacles. These meshes help us determine where the aircraft flies into trees. We will use a 50 by 50 foot mesh. Since turns out of the pattern are limited in duration, both time and altitude, the horsepower of the engine is assumed to be constant through the climb to downwind. These assumptions give us a great deal of possible flight scenarios. We will try all of the following scenarios to see which set of parameters gets us to the crash site below obstacle heights. I used the AEAT program to create all the obstacles meshes and flight tracks for all the different scenarios as Google KML files. These files were uploaded into Google Earth for display and analysis. Any obstacle mesh that occults a magenta flight path is evidence of an impact. Let's look at an example of a depicted impact. This slide depicts a flight path from the left, as depicted in magenta. You can see that the flight path starts out above the 85-foot obstacle mesh and then flies under it at the depicted impact point. This does not guarantee this as an impact point, just that it can no longer fly above 85-foot obstacles in that area. As you can see, all no-wind scenarios are impact-free. All other scenarios have 125-foot AGL obstacle impacts. Scenarios 7, 8, 10, 11, and 12 are impact-free at the 100-foot AGL obstacle criteria, albeit escaping by mere feet. All no-wind scenarios clear the 150-foot obstacle mesh, while all others result in impacts at that level. These results clearly show the effects of kinetic energy deficits on climb performance. The scenario that best fits the accident is S21. Commencing the downwind turn at approximately 50 feet AGL was obviously a major contributor to this accident. The view from the cockpit as you are approaching the crest of a knoll studded with 100-foot plus trees at a very low altitude may have resulted in a steepening bank away from the knoll back towards the airport, i.e. lower terrain, and a reflexive pull-up which probably would have resulted in a stall. The cognitive dissonance must have been extreme. You knew you could climb at approximately 1,000 feet per minute. The slowly rising terrain to the east would not appear to represent a major problem. However, that 1,000 feet per minute rapidly deteriorates to 200 feet per minute or less due to the kinetic energy deficits created by the changing flight vector relative to the air mass vector. This results in a constant need to increase ground speed to maintain a constant indicated airspeed climb speed. If you review the detailed flight parameters printout by the second, you see that ground speed steadily increases. The excess energy normally used for the climb must now be diverted to increase the ground speed of the aircraft, which results in a steadily lower VVI. Let's look at the VVI and altitude plot for S03, which was the no-wind, S21 the accident, and S25 the accident with 20 knot winds, respectively. This is the S03 no-wind plot for the VVI. As you can see, the VVI remains constant throughout the turn, and that you can see the altitude is steadily increasing in a straight line, which is exactly what you'd expect. Okay, this is the energy plot for the SO3 scenario. And as you can see, the total energy keeps going straight up at a constant rate, which represents the energy coming from the engine, which is constant. And the altitude increases, which is the potential energy at the same rate. And you'll notice that the kinetic energy remains constant all the way through the turn, because the speed is, the actual true airspeed of the aircraft never changes. And this, again, is exactly what we'd expect. What we're looking at now is the VVI plot for S21, which was the accident profile. As you can see, we don't get that steady climb in altitude, and we see that the VVI steadily decreases and then bottoms out and then slowly increases. And this is where we're starting to see the effects of this kinetic energy deficit, where it's got to start training that climb speed for putting energy into the aircraft. This is the S21 energy plot. Again, you can see the kinetic energy keeps going up. That never changes. But, the total energy keeps going up right along with what the engine produces. But we see some very different things now in the kinetic energy. It steadily keeps increasing because the ground speed keeps increasing. And, of course, the altitude at the bottom is not climbing at a straight rate as it did in the no-wind situation. This is a chart of the S25, which is the 20-knot headwind, and you can see that the energy deficit becomes even more pronounced the higher the wind. Okay, so let's see what this all looks like when we upload this data into Google Earth. As you can see, we can see the runway, liftoff point, the windsock, terminal, turn point 1, turn point 2, and turn point 3, which is where we actually use. And this is the S021 plot as it comes around. Here's Samat Street, and as you can see right here, right here is where we get impact between the magenta line and the 85-foot obstacle height, which is very near where the actual aircraft impacted the ground. Now we can also take a look, and we'll just bring in the 100-foot plot, and we can see it impacts starting about right here, which is a little bit sooner, which is what you expect. It doesn't guarantee an impact, but he's dodging, higher trees at that point. And then we can now roll into 125 foot, and you can see he's starting to dodge 125-foot trees all the way back to here. And we can roll into 150 foot, and he starts having problems in this area. So let's roll all that back and look at the 85 foot, and let's go ahead and refly that again, just like we did in the intro, so you can see what actually happened to this guy. And here we go. Pretty close to the treetops right there. And that's where you have tree impact. We can also do some other things that are very interesting in Google Earth. Let's get out of the ground level view, which is what it dropped us into. Let's go out and take a look at this thing. Google has, we can select the S21, which is this route, and we can show an elevation profile on this. And you can see, as we move our point here, that the red arrow shows you where on the track that it is, and you see the altitude profile. So this is a profile of that exact track, and you see it just keeps getting worse and worse and worse and worse and worse. And it's gonna, if I taken the track out further, the altitude climb gets even worse. What was probably screaming in this pilot's mind was, wait a minute, I should be climbing at over 1,000 feet per minute, but I am now climbing at 200 feet per minute or less, while maintaining V sub X. I must be caught in a downdraft. There was no way this pilot knew that if he rolled wings level and continued to just maintain V sub X, that he may have cleared the obstacles. Rolling wings level would have stopped the divergence between the flight and air mass vectors, thus allowing the excess horsepower to be rediverted back to the climb rather than being used to increase the kinetic energy of the plane. The largest energy deficits will occur with the strongest winds and the highest divergent rates between the aircraft vector and air mass vector, i.e. rapid turn rates. The more rapid the turn rate, the bigger the problem. Always use caution anytime you turn downwind quickly with a strong takeoff headwind component, have no excess energy, and are at a low altitude. The next video will cover the AEA tool and how it is used with Google Earth.